Our topic for today is section 8.3, which is trigonometric integrals. We'll here give you a little more precise guidance in the ways to integrate expressions involving trigonometric functions. And we'll have a few specific types to give you a very precise advice on what to do. So here they are. It's a little algorithmic section, type 1. So those are integrals of the form sine m to the x cosine n to the x dx. And then basically there are some fairly trivial cases, and then there's a little more complicated one. So if m is odd or n is odd, that's very simple. It's going to be basically, it's derivative ready in a way. The case that's a little more complicated is if they are both even. M and n both even. And we will show you the examples of both cases so that you see why are we saying that one of them is easy, one of them is a little harder. Integral of cosine cube x sine to the 4th x dx. So we notice immediately that there is an odd power, and that's your chance. So what do you do in that case? Basically, that extra 1 in the odd one is put on the side to give you derivative ready. That's the whole thing. So what you do here is, out of 3 copies of cosine x, you leave 2 of them, cosine square x, and then here is sine to the 4th x, and that extra 1 from odd part comes here. So generally, we are happy with the odd because when we remove 1 for derivative ready, the even one stays. That's the whole idea. Why? Because then we go for substitution, and underlying the expression is obviously derivative of sine x. So u equals sine x is substitution you cannot form. Why? Because du is cosine x dx. And you can say, but I can do that from even one. Yes, but what's good here is that this leftover has even a power. Because what? Let me show you an extra step, it will make more sense. So cosine x dx will be du. Sine is easy to replace because that's power of u. But cosine is only easy to replace if you have even power. Because then you'll say the following: cosine square x equals 1 minus sine square x, which is 1 minus u squared. If you had the odd power, you would get some radicals, everything would be very unpleasant. Here it is. Everybody was treated nicely, then just distribute, integrate, so get integral of u to the 4th minus u to the 6th du, which is u to the 5th over 5 minus u to the 7th over 7 plus c. And the last step is just to replace your sub back, sine to the 5th x over 5 minus sine 7x over 7 plus c. And that's our final result. So this was quite easy. And I'll do one more problem with the same idea, number 12. Although we usually think here of our powers to be integers, but the idea might work in non-integer cases as well. Sine 50t over square root cosine t dt. Once again, we are happy to have 5 here on sine. We are a little worried about this square root, but everything's going to work quite well. So we'll go, I better just prepare this better. So this would be sine to the 4th t, then square root of cosine t, and then extra sine t dt. So that kind of guides you quite clearly that our substitution should be u equals cosine t, because that's your derivative, so, or something close to it, so du is minus sine t dt. So now substitution works quite well. It will be integral. Here you get negative du, this minus goes to the other side. Then here is square root of u. It's all good. Sine to the 4t, as long as we have even power, could be nicely replaced. Why? Because sine to the 4t is sine squared t squared, which is 1 minus u squared, because that's 1 minus cosine squared. So that's it. So here it is, 1 minus u squared. And there are no trig expressions here. And I can say, well, how do I solve this? Probably it's fairly easy. If we successfully square this, then we can just do the splitting. Denominator is 9, so it should be straightforward if you remember our section 1. So this will be integral. I FOIL this carefully. 1 minus 2u squared plus u to the 4th over square root of u du minus its integral. What I use here is 1 minus u squared times 1 minus u squared is 1 minus u squared plus u to the 4th, which is exactly there. And now I can do the splitting, and I get power rules. 1 over square root of u is u to the negative 1/2 minus 2u to 3/2 plus u to 4 minus 1/2 is 7/2 du. Integral of u to the negative 1/2 will be u to the 1/2 over 1/2, which is 2 square roots of u minus 2 times u to the 5/2 over 5/2, which is 2/5, plus u to the 9/2 over 9/2, which is 2/9, plus. That's it. Then it might be nicer here, it's up to you. Of course, we have to substitute cosine back. It might be nice to factor out the root u so that everything inside is polynomial. So that will be what? Square root of cosine x goes outside. I'll do it simultaneously. What's left here? 2 minus 4/5. U to the 5/2, half is gone here, so 2 are left. So that's cosine square x. And plus 2/9. This is 4.5, half is gone, 4 of them are left. Cosine 4x plus c. Let's see, minus 2. What happened here? What happened here? I lost my minus here. Here it is. That minus is here, but I lost it in the second line. So then I need to switch all the signs. Sorry for this error. Minus is here, so it will be minus 2 plus 4, 5, and 9. So that was because of the lost minus. And what else? The other error is what? A variable was not called x, it was called t. So I better be accurate about it. So for these misprints. So here it is, because u should be replaced with cosine t, not with cosine x. All right, next problem will really address this unpleasant situation where, or less pleasant situation where both powers are even. So here it is, problem number 16. It is integral of sine to the 4th to theta d theta. What happens here? You can say, why am I saying that both powers are even? Because cosine is not there, but that means cosine is here appearing to the 0th power. 0 is even, so that really belongs to this case. So what do we do here? We cannot separate one copy of sine for derivative ready, but here's what we can do. We need a little help from trigonometry, and that's called reduction formula. And very often your trig professors tell you When they teach you this formula, they say, oh, one day you will need it in calculus 2. Here is the moment. Basically, there's a formula that says the following, that sine square x equals 1 minus cosine 2x over 2. And at the same time, cosine square x looks very similar. I think I mentioned it in one of the previous lectures. And really, if you add them up, you will get 1, and as you would expect. So they are very similar. One is with minus, one is with plus. Why is this such a great thing? Because square is not a good operation for integrals. Integrals don't like squares because they don't know what to do with them. We traded square for doubling the angle, and that's just a linear correction. So this is much easier to integrate than this. Unfortunately, we have fourth power, so we will need to apply this twice. Once to get rid of fourth power to get square, and next time from square completely to get rid of powers. So what would that be? So it will be integral of sine squared 2 theta, and then squared again, b theta. Then we trade, but be careful, my x is 2 theta, so that would be 1 minus cosine 4 theta over 2, and then square b theta. But then we keep going. By the way, 2 squared is 4 in denominator, so I can factor it out. So it's 1/4 integral. Now I square 1 minus cosine 4 theta, I FOIL again like last time. So that would be 1 minus 2 cosine 4 theta plus cosine square 4 theta d theta. Here it is. So these 2 were squared to give you 4. I pulled it out. And then when I square binomial, I use square or binomial formula. This expression is easy to integrate, just linear correction, but the square is bothering me, so I have to use now this formula and trade square for doubling the angle. So that would be 1/4 of 1 minus 2 cosine 4 theta plus 1 plus cosine 8 theta over 2, because double of 4 theta is 8 theta d theta. So what would that be? We are almost done actually. You see, I didn't do any integrals so far, I was just doing trigonometry. I have 1 here, and this 1/2 is 3/2 minus 2 cosine 4 theta, and plus 1/2 cosine 8 theta d theta. And now this is just table intervals with linear correction. So it will be 1/4 integrals of 3/2 d theta minus 2 integrals of cosine 4 theta d theta, and plus 1/2 integral of cosine 8 theta d theta. And now this is integral 3/2 d theta is just 3/2 theta. Here we have linear correction, integral of cosine 4 theta is sine 4 theta, but you need 1/4 that linear correction, so it would be 2/4 or 1/2 as well. And plus 1/2 times, again, integral of cosine 8 theta is sine 8 theta, but times 1/8 plus c. Here it is. We are done. Maybe the action to distribute, so it's 3/8 theta minus 1/8 sine 4 theta, and plus, this is 16 times 4, 1/64 sine 8 theta. Right, let's now do one type of definite integrals. It is a famous formula called Wallis formula. It is a special type of integrals. It's a definite integral. Let's consider the following integral. It's called Wallis formula. It is integral between 0 and pi over 2 cosine to the n of x dx. So this is a definite integral, and we don't make special assumption if n is even or odd. Obviously sign is missing, so n is even on its own. So there's an interesting way to calculate this integral, and we want to introduce a very important idea for mathematics in general, especially for computer science. It's the idea of recursive calculation. So what we'll do is the following. We'll call this integral In. So where n is basically the power above the cosine x. And here's what we'll do. We'll do integration by parts in a very somewhat strange way. So we'll get cosine n to minus 1x. We'll split 1 cosine x dx. And we'll use this cosine x dx to be dt. So we'll do integration by parts. So u equals cosine n minus 1x, and dd is cosine x dx. So du is n minus 1 cosine to the n minus 2x. The real cosine x is sine x, so minus. And v will be just sine x. So what happens here? Then we get what? U times v, so we will get cosine to the n minus 1x times sine x between 0 and pi over 2. And then plus, there is a minus from the formula and minus here, so we'll get n minus 1 pulled out. The integral from 0 to pi over 2 cosine n minus 2x sine square x dx. Actually, I was here a little bit careless. Why? Because this calculation is absolutely valid if n is greater or equal to. Because if n is 1, then you don't get like a 1 over cosine or anything like that. So we better assume here that n is greater than or equal to. So for all this calculation, n has to be greater or equal to. And then here is an interesting trick what we'll do. We'll actually, using trig identities, treat sine square x as 1 minus cosine square x. Or along the way, we'll just calculate this value here. When x is pi over 2, cosine of pi over 2 is 0, raised to a positive power, so that's all 0. When you plug in 0, you will get sine of 0 to be 0, so that first expression is just 0. Plus n minus 1 integral between 0 and pi over 2. This is cosine n minus 2x. Then in sine squared x is just 1 minus cosine square x dx. When we distribute, we'll get the following: n minus 1 integral between 0 and pi over 2 cosine n minus 2x dx. So I'm splitting the integral. Minus integral 0 to pi over 2 cosine to the nx dx. So what happened here? I actually got my beginning integral here, like in the looping method. And here I got another integral of the same form, but with the index that's lower by 2. So this gives me the following chance to call this is number in, and this number is in minus 2. And the same way as in the looping method, I erase this so that we have clean space. Like in the looping method, we get the following equality. We get in, I'll distribute now, equals n minus 1 in minus 2 minus n minus 1 in. And then we add n minus 1 in to the both sides, so we get n minus 1 in plus in is n minus 1, in minus 2. So we get n in is n minus 1, in minus 2. So we get in is n minus 1 over n, in minus 2. As long as n is greater than or equal to. So this formula doesn't calculate in immediately, but it calculates it in terms of the lower powers, and in a few easy steps we can get the results. So let me show. This is called a recursion formula, or a recursive formula. So here is an example how it's being used. Let me calculate I6. So if I want I6, what do I do? Instead of trying from I6 and reducing, I actually go backwards. So I go from I0 first. So I0 is integral from the 0 to pi over 2 cosine x to the 0 dx. Cosine x to the 0 is just 1, integral of dx is just x between 0 and pi over 2, which is pi over 2. So I0 has to be calculated on its own or memorized. Now what do? No more calculations, actually just recursion. I2, I'll use my box formula when n equals 2. So I get I2, 2 on the bottom, y on top, I0, which is 1/2 times pi over 2. How about I4? The same way, now I'll get here, when n is 4 on the bottom, 3 on top, 3/4 I2, which is what I had a minute ago, times 3/4. And if I want I6, I better put it on the side. What do I get with I6? It will be 5/6 in the same way as before. I4, which is 5, 6, 3, 4, 1, 2, pi over 2. By the way, sometimes we write this the following way. This is like a factorial, but you jump by 2. That sometimes people write that as 6 and double factorial. And this is 5 double factorial pi over 2. And that's how you use this formula. That's the example how to use it if n is even. What happens if n is odd? Works almost the same way. Let me just erase I. Can I squeeze it in here? Let me squeeze it in here. So that you can contrast them. Because odd ones, when you go by 2, end up with I1. So I1 is integral from 0 to pi over 2 cosine x dx, which is sine x between 0 and pi over 2. Sine pi over 2 is 1, so this is 1. So your start value is 1 instead of pi over 2, and then the same way. I3 is 2/3 I1. When it's 3 on the bottom, 2 on top. So that would be 2/3 times 1. Then I5 gets 5, 4, I3, which would be 4, 5, 2, 3, 1. So again, basically, what do we get on the bottom? 5 double factorial, 4 double factorial, but here not times pi over 2. So formula is the same, basically. You get double factorials in front, but then just at the end you have pi over 2 here, and you have 1. It's an interesting way to use that looping idea again, and also to maybe introduce or refresh that idea about a recursion. Then m to the x secant m to the x dx. What are the easy cases? You like this n to be even. The secant power. And you'll see very quickly why. And you like m to be odd, or m odd. That's all good. What's not good if both of them fail, so that means if what? N is odd and N is even. Then things get a little complicated. So here's an example, and you'll see why do we like it that way. Number 28, integral secant to the 6x, no, 3x dx. In general, the main reason why this works the way it works is that tan x prime is secant squared x. So you want two sequences for derivative ready and even left over. That's why sequences need to be even. And then derivative of secant x prime is tan x secant x, and that's why you need that extra 1 tan x, and then the leftover of tans to be even. So here it is. So that's the reason why they now behave differently. So if we see secant 6 3x dx, we say that's good because we have even number of secants and is even here. 3x is not bothering us. So what do? We keep 4 of them and take 2 of them for derivative ready. So what the whole idea is that this is someone's derivative. That's not my substitution, that's actually derivative of our substitution. So we go u equals tan 3x. So how much is du? Is secant squared 3x according to this, but of course times 3 for the chain rule, and then dx. So 1/3 of du is secant squared 3x dx. So we like that. So it's integral, this is 1/3 du. But then you can say, wait a minute, but what do I do with the secant to the 4th? As long as it's even power, it's easily tradable using Trig identities. Because another one to know, we also mentioned it, tan square x plus 1 equals secant square x. So if I want to trade secant square into tans, because tans are our substitution, then we'll get what? Secant square 3x is tan square 3x minus 1, which is just u squared minus 1. And I have secant squared 3x, I have 4th power, so that will be u squared minus 1 squared. Here it is. This is now absolutely basic. I pull out 1/3. I raise to the power, I'll get u to the 4th minus 2u squared plus 1. And then it's basic integral 1/3 times 1/5 u to the 5th minus 2/3 u to the cubed plus u plus c. We plug it back and we get 115 10 to the 5 3x minus 2 9s 10 to the cube 3x and plus 1/3 10 3x plus let's check trivial calculation 1/3 10 2 9. Why did I get plus? Oh yes, because sorry, secant square is tan squared plus 1, so it's plus 1 here, sorry. So when you square it, you get plus here, you get plus here, you get plus here. Exactly as we said. So secant square is tan squared plus 1, so it's the same way it's here. And that's how it works. Let's see the other easy case. And that is number 32. And that is integral of tan cube pi x over 2 secant square pi x over 2 dx. Generally, in this case, we can do also n even, but I want just to illustrate the other method, so it could be done both ways. So what are we going to do? We'll use the opportunity that n has odd power. So how does it work in that case? We again separate tan squared pi x over 2, but 1 tan pi x over 2 is left for a derivative. We are generally building this derivative. And it's always leftovers even, that's always crucial for Pythagorean trade. But this guy also needs secant of pi x over 2, that's not a big deal because that guy's replaced directly. So we spend one secant is left, as I said, that will be u, so that doesn't matter if it's even or odd. So this is tan cubed, secant squared looks good. And here is our, that's all derivative ready. So what do we do here? We then say what? U equals, not this is the derivative of your guy, so that's secant of pi x over 2. So du is secant pi x over 2 tan pi x over 2 times pi over 2 dx. Here it is, here's your package. So that's obviously 2 over pi d1. I'm better than notation, and I better focus on this. Tan squared pi x over 2 from here. That's secant squared minus 1. That's what a minute ago. Secant squared pi x over 2 minus 1. So that's what? U squared minus 1. And that's it. Everything is easily tradable. So this is u squared minus 1, this is u, this is 2 over pi du. Here it is, look how smoothly was everybody substituted at this point. We pull out 2 over pi, we get u cubed, integral is u to the 4th over 4. I'm rushing it here a little bit because right now we are all very proficient with that. Integral of u is u squared over 2 plus. So what would that give us? I can distribute that 2 to kind of make fractions a little lighter. So u, what was u? We call it back secant pi x over 2. So it will be 1/2 secant to the 4th pi x over 2. U was replaced with secant, so secant to the 4th. And those 2 quarters are 1/2. And minus 2 distributed on this 1/2, so that's gone, so I just have secant squared pi x over 2 plus c. So that was done quite quick. C. Here's one more example that works a little bit as a disclaimer, I would say. And that is number 42. What happens if these are negative powers if they appear in the denominator? So problem number 42, tan square x over secant to the 5th x dx. What happens here? Look, whenever you do a math problem, you don't run immediately for kind of algorithms and patterns that you remember. You always also need to analyze things critically. So what happens in this problem? This doesn't look reasonable. Why? because secant was invented to avoid denominators. So instead of writing 1 over cosine, we just write secant. So when secant is in denominator, it's in the wrong spot. So what? This is generally, I would rather switch that into sines and cosines because there's no reason to use these indented functions on the wrong spot. So what do? We trade tan, we know all that tan x is sine x over cosine x. So we get sine x over cosine x squared times a reciprocal of secant x to the 5th dx. So I'm just doing a little algebra. So what is this? Sine squared x, cosine squared x. This is cosine to the 5th x dx. So this is what? Integral of sine squared x, cosine cube x dx. So what I did, I just rewrote this in a much more reasonable way. And then it's like story from the beginning of the class. One of them is odd. These odd ones gives you the chance for substitution. So generally what are we gonna do? I better write that line. It doesn't hurt so much. Sine square x, cosine square x, cosine x dx. What is this? This is the differential of u equals sine x. So du is cosine x dx. Sine squared is just u squared, cosine squared is 1 minus u squared. So we get here, u squared gives you u cubed over 3, so it's 1/3 sine cube x minus 1/5 sine 5th x plus u. I rushed this a little bit, but right now, I assume that this is quite trivial. U to the 4th gives you 1/5 u to the 5th, you plug in back, and it's all straightforward. This is the part I wanted you to see. So don't torture yourself with tans and secants in situation where actually it looks much better as sine times cosine. And here is the real one. So this is the story when this will be, m will be even. So, and then secant will not be odd though, but it won't be there to help us. So here is the story. For example, we want integral of 10 to the 6x dx. So generally, you cannot hope that 10 will give you that extra one for secant substitution. So your only hope is just here to do the reduction. Or, I don't know if it's only, but only straightforward one. So what do we do here? We generally say the following. All right, this is 10 to the 4th x times 10 square x dx. What would that be? 10 to the 4th x times secant square x minus 1 dx. That's the trait from a minute ago. Then 10 square x is secant square x minus 1. And this is much better. Why? Because I like that secant square gives me derivative of 10, so that's a good substitution. And then, and that will go quite quickly. The other one gives us just a lower power, and that's also really good news. So that would be integral of 10 to the 4th x secant square x dx minus integral of 10 4th x dx. I will rush this one, you can do it step by step, but generally what happens, if you think of this as a u, I mean just 10x, this is du, so this is basically u to the 4th, integral is 1/5 u to the 5, so generally you can just say immediately that this is 1/5 10 to the 5x. As I said, if you want to write a couple of steps with a substitution u equals 10x, you will get the same thing. And then what do we do on the second one? Exactly the same trick. Because look at our benefit. From 6 we went to 4. Now from 4 we went from 2, from 2 to 1. That's how it goes. So what would that be? Tan square x times secant square x minus 1 dx. That would be 1/5 10 to the 5 x minus integral of tan square x secant square x dx. Now when I distribute, tan square x times negative 1 is negative tan square x, but there's a minus in front of it. So it will be plus integral of tan square x dx. With skipping steps, I hope you can follow that and recover them on your own. But just skipping steps, sometimes it's dangerous. You can mess up minuses or something like that. But I hope that you are grasping the main ideas, and that's what matters here the most. So 1/5 10 to the 5x minus. The same story as a minute ago. If 10x is u, you get u squared du. So you'll get the same way, 1/3 tan cube x. Now what do we do with this tan square x? The same story. We trade it the secant square x minus 1 dx. But now just straightforward. These are two table intervals. So we get 1/5 10 to the 5th x minus 1/3 10 to the 3rd x plus. Alright, I'm a little more patient here. Secant square x dx and minus integral of dx. And finally, here is the final result. 1/5 10 to the 5th x minus 1/3 10 cube x. Integral secant square is 10x minus x plus c. So here's our result. So what happened here, that's how we dealt with the fact that actually m was even. If m was odd, we would maybe try to trade it if he had secants. So that would be that nice trade. But since m was even, what we did, we traded 2 by 2 into secants to lower the power. So that was another interesting idea. And then one more method. You see, both these two types that we saw in the first part of the lecture deal with high powers. Powers are high, but the angle is the same. It was always just x. Because if you have x here and 2x here, they don't communicate well, you cannot do anything. So both two types deal, as I said, with the same angle. X here, x here. The same was in type 1 for sine x and cosine x. This is to the contrast with the following problem. Sorry, type 3. Here we don't have high powers, but we have different angles. So type 3. Product through some formulas. These are formulas that you learn from in your course of trigonometry, and when you study that, they probably also advertised that type of formulas for calculus 2. There are a few of these formulas. I'll just write one of them, and that is that sine alpha cosine beta equals 1/2 sine of alpha plus beta plus sine of alpha minus beta. First, if you memorize it, you memorize it. If you didn't, if you are not sure, does it come with a minus or what, it's fairly easy to check it if you remember your additive formulas for sine, because this is sine alpha cosine beta plus cosine alpha sine beta. This guy is sine alpha cosine beta minus cosine alpha sine beta. These two guys cancel, and you get 2 copies of sine alpha cosine beta. That's why you do 1/2. So it's very follows easily from your formulas, for additive formulas. The question is, why is this so good for us? Because when you need to integrate product, unless you have integration by parts, but that one's not helping you because you would just run in loops, then product is not easy to integrate, and the sum is. So you always trade it this way. There are two more formulas, and I'm not going to put them on the board, or I can actually. What? The other one is cosine alpha, cosine beta is 1/2 cosine of alpha plus beta plus cosine of alpha minus beta. And then you don't need all four of them. There's only a third one. So this is two cosines. You have a mixture. Doesn't matter who do you call alpha, who do you call beta. And then there is sine alpha, sine beta. And then that would be 1/2. Be careful when you subtract them, minus comes first. So here are three formulas that I used for reduction, and then whichever one is needed. So here it is. Example number 52. You do integral of sine negative 4x cosine 3x dx. Of course, you can pull out this minus from sine because it's an odd function and pull it out completely, or you don't have to because no one says that these angles must have positive constants or anything like that. So what you do here, you just trade this. So this is your. Be careful, alpha is the guy on sine. So this is your alpha. This is your beta. So this will be 1/2 sine. When you add them up, minus 4x and 3x, you will get negative x. When you subtract them, you will get first minus second will be minus 7x. Now I regret for not pulling that minus out, but it's okay, we'll survive it. So what then? Then really, I'd like to factor out that minus because they are odd functions for both of them, and then 1/2 out. So it will be minus sine x minus sine 7x dx, which is a what? Now I'll try, I don't want to factor out because integral of minus sine x is just cosine x. Integral of minus sine x is cosine 7x, but 1/7 for linear correction, and here it is. Maybe plus e, and that's the result. So it's 1/2 cosine x plus 1/14 cosine 7x plus c. So that is the result. So to summarize, we have, this looks a little bit like a cookbook. So it's not about big ideas so much as it is like we are learning recipes, how to recognize. So once again, you have sine and cosine of the same angle, but on high powers, and then there are easier cases and a little more complicated case, the same thing for tan and secant. And then third case has different flavor. It's a product of two functions on different angles, but powers are not high. So there's a plus and a minus. And you use reduction formula, product to some formulas.